Text Processing 101 with spaCy. Okay, so, and again, my name is Lisa Ong. I'm a lecturer and consultant at NUS ISS. I mainly lecture, I don't consult so much. Okay, what do I teach? I teach AI. I also teach edge computing, which has a lot of AI into small devices. And you can find out my profile on NUS ISS using this link, and you can find me on LinkedIn as well. Okay, okay. So, and I do have a GitHub repo, which is where we're going to get our source code from today. Okay. And basically, what I used to do was I used to work at Microsoft in Redmond, Washington, USA. And what I did was I did a lot of software development, and I did a lot of software engineering in C++. And then towards the end of my time at Microsoft, I switched over to machine learning, specifically using Python. So I've done a little bit of Python and C++ to Python interfacing in our machine learning libraries. And then since I joined NUS ISS, I've been teaching mostly in Python. So what we've been doing is we've been using all the Python libraries and just trying to solve problems and teach people how to approach different problems. So I teach that in a series of 4 courses, which will have details later. But basically, it starts you off with data and feature engineering, and then you do supervised and unsupervised learning and go into deep learning. Okay, so enough about me. So what are we doing today? So we are going to do in 2 parts. We're going to do text processing. And it sounds a little bit boring, but spaCy actually makes it look quite easy. So you can get quite entertained by it. Then we will do a little bit of hands-on. Then we'll take a break and we will do text meaning. So after you've processed the text, you want to know what is this text supposed to mean. So we'll look into word vectors, and this is where I think maybe half the audience will be a little bit scratching your head, but I will try to show you what they are, so that in the future when you hear the term word vectors and word similarity, you will have some intuition on it. And we will also do a hands-on. This one is quite fun as well. Okay, so that's what we have today. And I will try to stop for questions like sort of around these points after I cover a little bit. Okay, so let's do text processing. So text processing, tokenization, cleaning, and exploration. Exploration can be either extraction or just visualization. So extracting like nouns and adjectives and verbs, or extracting entities like person, place, or you're just going to just plot it and show people. Okay, so we'll cover these 3 steps. So before we do that, I think it helps to sort of set the context about what exactly are we trying to do here? What is the goal? So I have an example, a very famous example, I think, of Twitter sentiment for US airlines. So in the United States, after 9/11, the US airline satisfaction rate has dropped significantly because they started locking people down and they don't serve food anymore unless you pay. So there's a lot of negative opinions. So these do come through Twitter, because a lot of, if you've not used Twitter before, sometimes it can be a very negative negative place to be. So they get a lot of Twitter comments, you know, like for example, the one on the right, a little bit hard to see, but get me off this plane, I want to go home. So those kind of things. So what this project showcases is taking all these negative tweets, which to a human looks negative, right? When I say I want to go home, get me off this plane, it's negative, but a computer has to be taught. And one of the processes of teaching a computer is to extract the text. And before we can extract the text, we need to tokenize, we need to clean. Okay, so the steps that we are going to go through are the beginning points of doing this kind of thing. Okay, so that's one thing you can do. Okay, one journey you can start on. There are a lot of examples of sentiment analysis all over the web, but they do all start from raw text most of the time, unless you have somebody else's data set, but that's not so relevant. So another more relevant example, I think maybe if you use online banking, let's say you are a DBS customer or a Standard Chartered customer, you can actually use their bots. If you remember, there's a chat icon in your mobile phone or online, like it pops up Or even Ask Jamie, so Ask Jamie will pop up, right? When you're trying to look at something important, you look at your bills and then she pops up and she asks you, what do you want? What are you trying to do here? So these kind of things are chatbots, and they are in this very fast moving area called NLU, Natural Language Understanding. So it's understanding the semantic context of language. So it's not just NLP, which is natural language processing, where you just process the language and then you let somebody else look at it manually. It is actually having the robot or the machine, after processing, understanding the intent. So if you are curious, later on you can go to ibm.com and just search for Watson Assistant. They have a demo. This is my screen grab from the demo. So there is a robot, chatbot demo, where you can ask it, you can chat with it. He will prompt you to do certain things like, check for some fake credit card number. And then you just, so here's me testing using kind of a little bit of Singlish to test whether they understand what I mean or not. So unfortunately, this is very easy to pass because it just says next month and then whatever, it will just drop, right? So you can play around with it. It needs to be able to understand what you're trying to do. For example, I may not answer the question, right? When he say, when would you like to pay? I may be very bothered about I cannot log in or something like that. Then I will just type a response that is not related to the question. That chatbot needs to understand, like a human does, needs to know how to redirect, right? Because if it just continues and say, give me a date, then it's not responding to me intelligently. So keep an eye on this area. I think this is an area that is ripe for a lot of advancements, especially with Google just published a very ginormous language model, and a few billion parameters. So they're definitely accelerating here. But again, the beginning point is, I have this text, or mostly I have this text, it's raw. What do I do? I mean, I need to do something to convert it so that the machine can understand, right? So this is what we'll cover today, okay? So here's sort of the workflow that we will go through. We will actually stop roughly, we won't spend so much time in the analysis part because that is very broad. We'll do a little bit just to give you a taste. By that time, it will be 4 p.m. already, so you probably want to log off. But we will look at this part. Collecting a raw text, I won't cover so much too, because it's really about crawling, getting big data sets. So that's sort of out of scope of this talk. We were going to focus a lot on these two in the center, which is processing the text and extracting the meaning. Okay. So here's what example of a raw text. Okay. So on the left-hand side, I think you probably recognize who's the author. Okay. And then on the right-hand side, the author's face is there. So raw text is very, it's not constant. It changes over the years, right? So when Shakespeare wrote Hamlet, the way we talk, the way we express ourselves is different from the way we express ourselves today. Or maybe, this is 2016, I think, or maybe before that, 2012. Yeah, so he got re-elected 2012, so this is 2011. When, people just type very straightforward things in Twitter, and maybe it may not even be the word for, it may be for, and then it'll be short form years, right? So language is not static. Unlike a lot of other things, like maybe other type of data, financial data, maybe different formats, language changes a lot. Changes with the person, it changes with generations. How I talk is different from how my parents talk, for example, because I went to the US and they didn't. So it's like we use different words, we express ourselves differently. So models do need to be created and refreshed. And I want to add another thing, it needs to be customized as well. Okay, so this is example of raw text. And then more examples of funny raw text. On the left-hand side is emoticons. And on the right-hand side is text that is not in the order that we usually look at, right? For example, vertical text from right to left. So the good news is emoticons do get handled. They usually are using a specific language model, and we will explain what language model is. Okay? Or if you want to use existing one, you can modify your language model by adding just some rules. For example, if I look at this text sequence, parentheses with this funny figure, this. So there's this 1, 2, 3, 4, about 4 or 5 characters, right? I can put a rule that if somebody types in this sequence, it means they are smiling like Mona Lisa, that kind of thing, right? Or this person is very shocked. So these are the good news about emoticons is they tend not to, they're quite static, right? Of course, new ones get invented, but you can always add new rules. And then the good news about this is actually not part of the text. It's an attribute of how the text is displayed. Okay, rendering attributes. So you can most of the time have very good parsers that extract it. Like if the attribute is part of a HTML tag, you will just delete the tag and just focus on the text. Okay, so we are really mostly looking at the content, the content of the text. Okay, now I'll have an example of a mixed English and Chinese text later as well. Okay, so we're going to go through these steps for processing text. We're going to select the language model, split it into tokens, and we're going to clean and explore the tokenized text. Okay, so I'll pause and check for any significant questions. Okay. So the poll is an example of text processing. Yes. Well, it's more like text clustering and text grouping. Yeah, yeah. Good. So we're going to look at this part now. Okay, so first part, language model, right? Language model is going to be, it's not specified explicitly in my process, but it's actually going to be applied in these two sets. Okay, and then as part of processing text, we're going to do these two tasks. Okay, so that's where we are. So text processing, this is the same information before. I just try to organize it a bit more. So we're going to cover these 4 things. Okay, so selecting a language model, we have to identify basically 2 questions, basic questions. What is the primary language being used, okay, for your text? For example, the primary language of this slide is English, right? It may not always be. English is also a lot of the default language models that people assume, but it may not be appropriate, right? It may be that this is in Malay, but it's Romanized, right? So somebody has to identify what the primary language is. There may be a way to automate this through AI, like do a language classifier, but that's sort of, that's an extra thing you want to stick in the beginning. Okay, so you have to select the primary language. So you have a list to select from, and you have to check which one is supported by the tools. So for example, spaCy has not just this, spaCy has a few. So I'll send a link to the chat so you can look at it. Okay. Give me a sec while I type this. I hope this link works. So this is the link that is on my slide. So if you go to that link, you will actually see a group of language, a bunch of language, more than the ones I show. Okay, so you will see that there are languages that have 3 models and the languages that have no models. Okay, languages that have no models are on the list to be developed, but they are waiting for someone to integrate into it, someone to find the data. So language models are not cheap. Okay, language models require a lot of data and time investment. There may be ways you can just use an existing one and adapt it. We won't go into that detail today, but I can share with you a very simple tutorial from spaCy about that later on. So most of the time, if you're dealing with just standard text from newspaper, you can get away with English models. If you are looking at Twitter, for example, Twitter will be a little bit challenging for spaCy. You will go into a NLTK. NLTK has a spaCy Twitter language model. So when you are in doubt, just Google the type of, like domain, like Twitter language models, and you will be able to find specific ones. So you need to sort of know what the primary language is. Okay. So, so that's that. Okay. So I think Malay and Hindi are still on the list to be supported. But the good news is Chinese is available today, so we can try that. So I'm going to do a Chinese versus English just to show you how you can sort of jump between language models very easily. Okay, the process of training a language model is very difficult. It's quite sad to see the GitHub track. So GitHub has a language model. You know, I want to train this language model, and then you have a lot of experts from different fields trying to train it, but integrating it into spaCy has been quite tough. Okay. So a question earlier, or from myself, I guess, what about text like this? So what do you do? Okay. So earlier on, I had English, right? My slide was English, but now my slide has Chinese. Let's assume this is actually text in Chinese. So this is a Amazon posting in Amazon China. Has Chinese, then alphabet, and then Kindle. I apologize for those who don't read Chinese. You can just, just know that it's some characters, and then the word, that there's a mix of Chinese and non-Chinese characters. Okay. So what do we do here? Well, most language models, unfortunately, support only one language per model, because to support a language alone is already very, it is a lot of work, right? It's a lot of data. We saw earlier that language changes. So if your model wants to be generic for conversations, for text messages, for newspapers, for web, right? It needs to encompass everything. Then even with one language, it's already sort of struggling. There are multi-language models. So if you are sharp-eye and you went to the spaCy webpage, so let me show you. Okay, so the link I showed just now, spaCy.io usage models. If you are sharp-eye, you will actually see there's a multi-language. So it looks hopeful, right? Well, it supports certain things only. Okay, so most of the time people will use, let's say they pick Danish, and then there's some English words I need to add to Danish, right? So I would hope that the English word is, I would check to see if it's inside the vocab. Okay. I think someone needs to mute. Sorry about that. So you check if it's in the vocab, and then if it's not in the vocab, you can check the spaCy documentation on how to add it. It should be quite easy to do. Okay, so if I scroll down, you see that the top ones have 3 models. We will talk about what are those 3, but once you start going down to the more less common, I guess less Romanized languages, you will start to see there's none yet. Okay, right? So they have this very promising list, but not completely fulfilled, and this is considered a lot. Okay, NLTK similarly also has language models. So what people do is, if you are like wanting to work on something in Hindi, for example, you need to talk to someone who, some NLP researchers or someone who knows how to train a Hindi model and work with that person to do it. Okay, so it's still not widely available as of yet, but there's always hope. Okay? Especially if there's more and more experts in this area. Okay? So the good thing about spaCy, if you learn spaCy, you will start to become one of the experts, and you can maybe eventually help people train model or help people collect data. Okay, so this is a summary of what I said earlier. Most models only support one language. There are multi-language models, but they are limited functionality. Once you start using it, you will realize you run into quite a few problems. So some borrowed words like Kindle can appear in the Chinese vocab if it's common, like if they don't have a Chinese word for Kindle. So you can train it using, by updating the model, or you can handle it to rules. So every time I see this character sequence, it means Kindle, right? So something like that. So briefly, how the models are trained. They are usually trained with a ginormous text corpus, okay? Hundreds of thousands or millions of words. I think the English one that we'll look at today is trained on 2 million words or more, okay? Fortunately, you don't have to train from scratch if you are using English and you just want to change a bit. You can just incrementally update it. So what they do is they take a vocab and they encode the words into numbers. Okay, so the text will have to be encoded. I will talk more about this later, but there are basically 2 approaches that are used. Okay, one is to count probabilities and try to maximize the probability of a word appearing, and one is to use neural network. Okay, so I'll come back to this later, but it's just to show you, give you a flavor of how it's trained. Okay, so they take a lot of text from many sources, and try to take the text and run it through these algorithms, generate some vectors, and then also, in addition to the vocab, okay, the encoding, they also create some rules, okay? So they either use the rules manually, create it manually by, let's say, if this word follows that, if it's an A after, you know, if it is plural, I add an S, those kind of thing. Those can be done manually, or they can train classifiers for it, okay? Sorry, this is cut off, but there's basically a link to how it's trained, how the name entity recognition is trained, okay? I will give more examples about that. Okay. And then after you've stopped at step 3, right, you have a model already. So the one we download today, right, it's basically up to step 3. Then step 4 is if you choose to do so, you can update the models. But a lot of times you don't have to. Okay? You can add custom rules. So this is the spaCy matcher. There's a simple way to add it, how to match characters to particular tags or particular rules. How to process when you see a particular sequence, or you can use their update to fine-tune their neural network. Okay? So basically fine-tune the word to vector part so that this is updated and this is also updated. Okay? So that's how they are trained. Very involved process. Okay? So so the first thing after we selected our language model, right? Let's say we say, I want to use the Chinese model because I have a lot of Chinese text I want to process. Then I'm going to apply the language model to do tokenization, cleaning, and extraction. Okay, let me check for questions. Okay, good. All right. So what is tokenization? It sounds like a very big, difficult, big word. But actually, it's just, if you look at, follow my mouse pointer on the left first, it's splitting a text into small chunks, okay? And the chunk is usually word, okay? A word. So in this example, this is the national pledge. I think, so if I want to tokenize this text, right? Let's say I am able to read this into my computer and I have a text file, okay? So I can tokenize it by words. So my first token will be dear, second word will be pang, boon, fourth word will be sorry, and then all that. So I will split it into by space and by punctuation into chunks, okay? So that is the process of starting to process the text, okay? Why do we do that? Well, we want to maybe apply different rules for the word dear versus the word sorry. We may want to treat these two tokens as a name because it looks like a name, right? So those are the basic building blocks for this kind of thing. You need to recognize the date. So it is how a machine looks at things is it breaks it down into small blocks, okay? So that's, so we'll talk about, so when you think about that, the token boundaries are space, okay? So that's one way. Actually, there's multiple ways. So another way you can do this is by sentence, okay? So you can also break it by sentence. So you say, first sentence is sorry for the delay, blah, 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 stop at 1966, one sentence. Sorry, first sentence is dear Pang Boon. Second sentence is this. Third sentence is this, right? So you can also break it up by sentence. However, most of the time, sentence is like a higher level representation. You still need the token to understand the sentence, okay? So the small unit is usually text, is a word, okay? So that's tokenization, okay? Breaking the text down into small chunks so that we can start doing processing. So English is usually space and punctuation. These rules, you can actually write them yourself if you are a programmer. You can write a regular expression to pass this, but that means you have to be responsible for coming up with all possible rules in order to handle any text, right? So rather than doing that, it's more advisable to just use libraries so that you can spend more time working on the application, okay? So we will see how to do tokenization. It's very easy with spaCy. Then after you've breaking up the text, right, then you do cleaning and extraction. So the next few slides will be my last few before we jump into the hands-on, so we can actually see concrete examples of these, okay? But if you can bear with me for the next few minutes, we will just cover the high level of this. So cleaning, what is cleaning and what is extraction, and then we will go. Okay? So cleaning is removing irrelevant words and tokens. Okay? For example, I may not care about punctuation so much if I'm trying to find the, just try to see the meaning of the text. Okay, extra spacing, definitely, you know, sometimes formatting, Word likes to insert extra spacing or something like that, and you know, it doesn't mean anything. Symbols, sometimes bad symbols get inserted, or maybe it's an emoticon that you don't really need. And the last part is the interesting part. So this is the notion of stop words, STOPWORDS. So stop words is a term to mean words that don't really add to the meaning of the text, right? So in other words, right, the word is, the, a, and that, right? If I were to read this sentence, let's find a sentence. This is a very long sentence. Okay, syntactic relationship, words that come before, after. So if I drop the word that and or, okay, I still have roughly the same meaning. Okay, words come before ancestor, after child, current word, right? The word or and the word that are sort of not, maybe the word or can mean something different, but the word that is really redundant, for example. Okay, so another example, this is a sentence. So the word a sentence, or even is, these two words, is and a, actually don't bring much to the meaning of the word, right? In fact, this is these three are stop words in spaCy. So if I just have the word sentence, you know that this is sentence. Okay, so the meaning is already captured in this noun. So when we process a huge amount of text, we try to squeeze as much of the irrelevant stuff out, so we don't take so much time processing them. Okay, and so on. So we will see examples of that. Okay, so cleaning, basically, besides removing the obvious things like punctuation and spacing, symbols, we also remove subwords. Okay, and then after that we do extraction or exploration. Okay, looking at part of speech, which is, you know, this word is a verb, sentence is a noun. We can also look at entities, right? In this case, there's not really an entity here, but for example, just now, the example here, right? So entities, the word Singapore is a country, right? So it's not a word. Singapore represents more than just a word, it's a country. Just like name, right? This is not some two words happen to be add together. They're actually a person's name. So this will be identified as dear person, and then letter is a noun, and all that. Replying is you know, adverb and things like that. So you can identify, and this is a date. So those are entities. Okay, very useful things, because if you're trying to figure out intent, like, is this person, you know, is the chatbot is trying, if you are writing a chatbot and the chatbot is trying to find out, is this person, customer, asking about his credit card or asking about wanting to talk to customer service, right? You need to identify the noun there to see, and then you check if the noun is a credit card or a noun is about customer service, so things like that. Okay, syntactic relationships, another way. It's a richer way to sort of tie in words together, how they are related to each other. Okay. Okay. So this is the sort of the list of the part of speech that spaCy supports. Okay, adjective, apposition, adverb. So your primary school, secondary school English lessons start coming back. Okay, I had to look up what a determiner is. I didn't remember what that was, but I remember nouns. Okay, so you can identify this using the tool. Okay, so you don't have to write your own examples, write your own rules. That's really, really cool. Okay. Name entity is like recognizing what are the entities, like nationalities or religious political groups. So Singapore, it's like this, I think, or it could be a place as well. Event, you know, so these are the things that I can recognize, extract from the text. Okay. Okay, so time for our hands-on. Time check. It's about 2:45. I've spoken for about 40 minutes, so it's just nice. We're going to look into loading a language model, tokenization, and cleaning exploration. Okay, so next two slides will show you what tools we're going to use. Okay, first one is spaCy. Is what you are here for. It's a popular open source library. The word CY comes from Cython, which is a C accelerated. It's a fast C version of Python. Okay? It's basically if you want to run Python faster, right? You actually run Cython. Okay, so spaCy needs to be very fast because it needs to handle large volume of text. It's good for beginners. It's very extensible through pipelines and other things, metric and rules. It supports many models. So it's not just a very basic NLP library. So when you select an NLP library, you want to find something that other people can, that you can use examples from other people. You can share your findings, and you can also find a library where people can collaborate to build rules for models like these. Okay. So language models are downloaded very easily like this, and then we just load them. Okay. So let's see an example. And then we also run things in Google Colab. So Google Colab is a web browser based application that we run, allows us to run Python. It comes with pre-installed libraries, including spaCy, but we are going to upgrade the spaCy on it so we can use Chinese models. These are usually Linux cloud machines running some flavor of Linux. This is from Google's cloud. And the last bonus is it's very popular nowadays with machine learning because it includes free GPUs. They are not the fast GPUs, the very high cutting edge ones, but they at least are faster than your laptop. Okay, so we'll do those things. Okay, so let me announce this link so that you have a chance to go to this link while I answer questions. So I will also post the link on the chat. Okay. I don't see any questions, so I think we can just keep going. Right. Oh, thank you, Yaming. Okay, so click on the text 101. Okay, so I'll show that. I'll switch over to that right now. Okay, so if I go to bit.ly ISS text 101. So time to move your fingers a bit. Okay, it's getting to be 3 o'clock sleepy time. So here takes you to the GitHub repository, and here's a button here, okay, that you can click to open in Colab. Okay, so this is the notebook that we'll walk through. The one that is on the website is just a static rendering of it, so you cannot run anything. Okay, so what you want to do, if you can make it more interactive, especially later when you try on your own text, click on this button. Okay, if you click on this button, it will take you to Google Colab. So Google Colab, currently I am signed in. Okay, so I'm signed in as myself. So if you are not signed in, you will still be able to see it. It's just when you start running things, it will prompt you. It will say this notebook is not from Google. Would you like to run it? And then you say yes, and then you need to log in. So the login process is just like logging into any Google service. Okay, it's free. And it also gives you a way to start developing on Google Colab. Okay, and Colab actually comes with a lot of help videos about how to use them, how to incorporate different renderings like images into it. So it's quite useful. Okay, so we're gonna just look at part 1, right? And then I'll do a break. I may do the break early if I see that time is running out. Then we will come back to part 1 and finish part 2. Okay, so this is really what we'll see today. So there's a little bit of background how to run this. So you see there is a connect. Okay, so you can connect to a hosted runtime that will start it to connect to Google, or shortcut is you just scroll down past the text explanation and then just click on this button. Okay, run cell. Okay. So above that was just some write up, but here is where we want to start. Okay, so you need to run these in order. Don't jump around because then you might get errors, because everything is running in sequence. Okay. So first thing is we're going to install spaCy 2.3. spaCy is included in Colab. However, the version that they have is 2.2, which doesn't have the new models. Okay, so Google does provide some pre-installed libraries, but they try to pick the most. They don't upgrade it so often. Okay, so we're gonna run this. So when you run it, you see there's a warning. I hope the warning shows for you. just click run anyway. Okay. So it will run. Now you see on the right hand side while it's running, it will show this little progress bar, but it's actually initializing on there. Okay. It's connecting to a Google Compute Engine backend. Okay. And it has, quite a bit of RAM, quite a bit of disk. This is a Google Cloud machine. So the power of Colab is you don't have to go in and provision your own machine, pay for some minutes or cycles. You just come into Colab and you click this run button, it will do everything for you. Okay, so that's why it's so popular. So we installed spaCy 2.3. So this is just how Python libraries get installed. Okay, so we'll keep going. Okay, now we'll load this model. Okay, I need you to load the medium model. Okay, because we will be looking at word vectors. Okay, so while you are clicking this and it's downloading, it takes a while. It's about a few megs. Right, I'll show you what I mean by medium models. Okay, so but before that, so there's some references here for those who are new to programming. Not everything in this will be understandable to you right away, but there's some very useful cheat sheets for the different libraries we are using, so you can refer to them. Okay, so we're going to load a language model, we're going to tokenize the text, and we're going to clean and explore the text. So starting with language models, we'll get the English and Chinese ones. So here's the write-up, the 3 sizes of language models that are usually included for languages that are common. So we have on this table English and we have Chinese. Okay, so the small, medium, large is just the size, not just the size of the model, but how many words it supports. Okay, so English is trained on these 2 corpuses, and Chinese is only trained on this. Okay, so I shall click this list again, and I'll show you the details. Okay, so if you ever want to find out more, and it's actually quite an important step to take because it's you want to know what you're trying to load, right? So let's just look at the English one. Okay, so if you click on 3 models, available pre-trained statistical models for English. So this is part of spaCy. They have already trained it, done the work. You just need to download it. Okay, so this is a multitask convolutional neural network trained on nodes. Okay, so there's some details. What is it? It includes vocabulary, entities, vectors, and syntax. Okay, this is important. What is it trained on? What can it handle best? Okay, it can handle written text, it can handle news, blogs, comments. It may not be able to handle conversational text, for example, and that you may have to find another tool, maybe look at whether someone has trained their own model for it, or maybe look at NLTK. Okay, it's quite big. This is considered small, okay, but this is at least the minimum to support this. I think I forget what the size of the vocab is. Okay, okay. So this one doesn't include vectors. Okay, we want the one that includes vectors because we do want to learn more about the word meaning. Okay, you can still use the small model for basic tasks like tagging, parsing, and it does come built in. Okay, so onto nodes. All right, just to give you a flavor of it, it's a UPenn corpus. Okay, that is basically a lot of web conversations. It supports both English and Chinese. Okay, okay, so telephone conversations, newswire, newsgroup, broadcast, web blogs, supports English, Mandarin. So if you have so most likely the Arabic model, if there's one, can also be trained with this. Okay? So Chinese and Mandarin Chinese sort of different. Okay, probably one is common and one is 中文. Okay, so and there's like the different amount of data, medium, how many words there are in different areas. Okay, okay, so this is what's being consumed, and then the medium model, which is what we're going to load, is about 3 times larger. Okay, now this is the one we want. We want 685 keys, so 1,000 keys, so it includes a vocab of this size. Okay, the earlier one is smaller. Also includes the vectors. It also includes common crawl, okay, which is another popular corpus, right? So it can handle more things. I would say if you start with any non-trivial task, you still start at least the medium one. And there's also the large model, which is 700 megs. Okay. All right. Okay. So the difference between the medium and the large is how many different unique vectors it has. So what they probably did here is they tried to just sample the vectors for the top 20K. Okay? Top 20 most, 1,000 most frequently used words. So that's what here this is. Okay, so we've installed this. Let's continue on with the Chinese one. So they are separate downloads. Okay, so one model per language. Okay, so oops. While we're doing this, let me check if there are any questions. Yes, you can download and run on Jupyter Notebook as well. But for convenience, because the libraries that we are installing may not be available on your computer, you may have to install it slowly. You can maybe easier to follow if you just use the notebook on Colab. Yeah. So if you want to download this, you can always go here and download this. You can also download it as a Python script for those who are savvy in this area and don't like to deal with the click, click, click. Do both. Okay. Okay. So very important thing after this finish, okay, I need all of you, if who are following me, to do one very important step, okay, which is to restart the runtime, okay? But wait for this to finish first, okay? Otherwise you restart for no use, right? So what happens is these are installed as extra Python libraries. Because these are extra Python libraries, the current Colab that we are running doesn't know they are there. Okay, it doesn't know, so we will get an error. So I'll only demonstrate the error for you. Okay, so if I don't do anything, if I don't follow my own instruction, right, and if I run this and then I run this, okay, I will get an error that looks like this. Okay, so this is what you want to avoid. Okay, so basically it says I can't find the model, blah blah blah. It doesn't seem to be a link, but I'm like, I just installed the model. What are you talking about? That's because this is not that smart. Okay, so how do we do this? This is a common practice but not common enough. So we just don't do runtime run all, do runtime restart runtime. Okay, so I'll keep my mouse pointer here for a little bit longer so you can go to this. Okay, so this will restart the runtime. Okay, and then it'll ask you, are you sure? Are you sure this is really scary? Actually, not really. All it does is it just restarts the Python, whatever Python that was running. Okay, so I still have my machine, I still have my data. Okay, so say yes. Okay, so now I've restarted the runtime. Okay, so you'll see that this will say initializing, then you reconnected to another one. Okay, so then I import spaCy, and then I run this. So before I had this error E050 whatever, now it should work. Okay. Yeah, so it loaded the model, right? So you're able to, it's a little bit anticlimactic, but it usually is when things work. It's when things don't work, it becomes a big hassle. Okay, so remember to restart the runtime. Okay, remember to, if there's nothing you do later, pay attention to this part. Okay, okay, so now we're gonna really do tokenization. Okay, so we're gonna try both English and Chinese text. I already have the text inside, so you don't have to go and find yet. So we're gonna look at tokenization by word and tokenization by sentence. Okay, tokenization by word. This is from spaCy's course, which is a really wonderful course if you want to learn more about spaCy, free. They have this nice diagram. So we have on the top a doc. Okay, doc doesn't mean doctor; it means document. Okay, document. Document has multiple words. So it has I love coffee, which happens to be true for me. I love coffee. So here, word tokenization just says a token is the word I. The next one is the word love. And the next one is the word coffee. Okay. And then there's other attributes about it being a pronoun, verb, noun, and then there's some relationship. You know, this is the subject for this verb, and this is the noun for this. Yeah. But the key point is tokenization by word is you take the word, you chop it up, but you take the text, you chop it up by word, right? And then internally, this is what spaCy does to map this word I to some vocabulary. So their vocabularies are stored in like index, some kind of numbers. So don't worry so much about what the Lakshmi is. Later on, if you want to, this is more advanced usage of spaCy. It's how they store their strings and their tokens. So the reason why they do this is they don't want to store the word I. Let's say my text has 50 instances of I, because it's all about me, right? I love this, I love that, so a lot of I. If spaCy stores a string for every single one, then there's going to be 50 duplicates, right? There's going to be 49 duplicates. So what they do is they just use numbers to reference back. Okay, so that's just it. So here's where the first thing we're going to do here. So I took this when we were a few days ago. This is from Channel News from Straits Times. So I have this text. Okay, so this text is actually, if you're not familiar with triple quotes, it's just a long string. Okay, so I can paste spaces. I can paste a raw text in here without worrying about extra space. Okay, so if I were to use the non-triple quote, then I need to make sure there's no new line. Everything needs to be in one line. So what we do is we have an English text, okay, and then we paste the text in here between these two quotes, right? So I start with this, no text, right? Then I put this is a text, right? I can do it this way too, okay? So if I take this text, I go through, so this is the magic for spaCy, but basically spaCy has this NLPEN thing, which I've already loaded earlier. If you remember a few cells before, I loaded the models right into this, okay? So this is spaCy's starting point, okay? And then text is my text. So I'm just going to process it using spaCy. Okay. So if I do that, then you see that it has tokenized my word. This is a text. Okay. You can try around. I'll give you time to play around this later. But I wanted to give it a more complicated text, like few lines. Okay, so jobs are available for Singaporeans in Infocom. So I just pasted it directly from Straits Times. Okay, ran this text through, and now looked at the tokenization. Okay, so a little bit of explanation on this syntax. So basically, this is called list comprehension. Okay, it's a simple way to create a list. Python using one line. Okay, it's a fancy way of doing it. Okay, you can Google list comprehension. If you're not sure what it is, it's a very neat syntax because it's just one line. Of course, one line doesn't mean it's that cool if you're not a programmer. So basically what it does is for every token in this word, I'm going to just return it. Okay, so I'm returning it. The first one, jobs are available. Okay, so that's what it's doing. Okay. So if you want to impress people with your Python skills, right? If you're sort of budding learning Python for your next career or your next move, definitely do pick up comprehension because it shows that you actually know enough of the language. Okay. Yeah. So I'm going to hide this so we can go on. So sentence tokenization is a bit similar, but uses a different way. So earlier on, I just take the whole thing, which comes from where? It came from the, when I process using spaCy, right? Okay, these 3 lines. So it came from here, right? .en came from here. It's basically a document object in spaCy that I can do a lot of things with. Okay, I can just get a token from it this way, or I can get sentences from it. Okay, SENTS is sentences. So a cool feature about Colab is if you hover, sometimes if you hover, you'll get more information, sometimes you don't, okay? But it's supposed to give you what this is. But anyway, so if you run sentence tokenization, same thing, same list comprehension, but it's for sentence for S in sentences, print it out. So now you see that, hey, I have a list of sentences. Okay, this is the first sentence, right? Is that correct? First sentence. Yeah, because that's where my full stop is, right? It ends at Balakrishnan. Okay. So, and then the next sentence, okay. Now this one is interesting because I think there's a typo in the newspaper. There's an extra dot here, but for some reason, actually no, it's correct. Let me see how many sentences there are. Okay. Let me just check. I'm just curious now. 5. Okay. So is there 5 of these? This is just counting how many there are. Okay. 1, 2, 3. Oh yeah, this is the 5. It's just the printing of this thing is actually, yeah, this is 1 sentence. So it includes the full stop. So I have 1, 2, 3, 4, 5 sentences. This one looks like it's in the next line, right? Because there happens to be a new line here. Happens to be extra space here. Yeah, see, COVID-19 accelerated this trend. Then there's a giant new line here. Okay? You can of course delete this, but I'm just doing it with raw text, right? I'm trying to minimize the amount of processing. So we've already done the first step, tokenization. Very easy, right? Let's look at Chinese. So apologies again for those who don't read Chinese. I just took this from the Chinese newspaper. Again, I just took the first three sentences. Okay, same thing. Now, important point, you can't use the English model with it. Okay, you have to use the Chinese model because then it can break it up into the correct words. Okay, so let's say if I run this, okay. So this is, again, I'm passing the text in, right? Calling this language model, which earlier on I had already loaded, right? Okay, loaded. So I have my result. This is the document object. Very important thing, right? Everything will hinge on this guy because all the intelligence is here. Okay, this is the document object. So the first thing I can get the tokens from it. So the so you see that it has actually done something intelligent. Okay, so for those who read Chinese, this is a word for this year, and then this is another word. This is a word for August, and this is 9th. So it's talking about August 9th, okay, National Day. Okay, so if I did the wrong model, so let's say I wasn't paying attention, right? Then I did the wrong model because early on I had loaded the English one, right? If I put the English model, I'll show you what happens. Okay, it's not EG, it's EN. Okay, so this is the wrong model. Okay, so if I pass it, I don't get any error, but when I do tokenization, it couldn't find a space, couldn't find a space, couldn't find a space. So everything, it treated this as one word. Okay, so the wrong model can result in disaster. Okay, so let me restore things back. Okay. So we've tokenized in Chinese words. Can we tokenize Chinese sentences? Okay, yes, same thing, same pattern as before. Just remember use the right thing, right document. Okay, so when you run sentence tokenization, for each sentence, print the sentence out, you will see something like a sentence is separated by this little symbol is the end of sentence in Chinese. Okay, so very easy to see end of sentence. This is probably a very simple rule that they just program. Okay. Although this guy is being treated as a sentence, so there's some problem here. Okay, there's some issues with this model. You see that? It's treating this as a separate sentence. Yeah. So you may have to, if this is an issue with you, you may have to detect this. For example, you may have to detect the existence of this character and just do, okay? And just combine these two. Okay, so last part, and then I'll take questions. Okay, so we tokenize. Now we're gonna clean. Okay, so each document contains a list of tokens, and then we can clean them and discard the ones we don't need. Okay, so for example, going back to the English example, for example, the word, if I don't read the word and in and the, right, and for, if I say jobs available Singaporeans Infocoms, it's actually similar. A human can understand what it's trying to say. Okay, so I can remove those words. I can also remove the punctuation like comma, okay, or this quotation mark. I can remove, right? Those things, those don't really add to the meaning if I'm trying to just get the meaning of the word. So that's the thing we do. And now because we have per token, we can actually clean the text. Okay, so this function looks a bit complicated, but really what is it trying to do is it's just trying to take in the input text, do the same doc equals NLP thing. Okay, I'll pass in the model. So we get our document. Everything starts from the document. Then it's this line here. Okay, so earlier on we had just T for T in doc. Okay, earlier we just did this. Okay, and then we do every token. Okay, so how do you not do every token? How do you add condition? Simple. You just add this condition. If something, something, something. Okay, so do you see this? This is a condition, right? So before that, if I don't have the condition, everybody will be returned. Okay, so let me demo that. If I don't have the condition, right, everything you see jobs are available will be returned. Okay, right? So everything is there. So let's say if I want, so if I were to just slowly add it back. Okay, so let's just do no punctuation. Okay, so let's make sure I have punctuation that I can see that it works. So there's a punctuation here. Okay, right? So if T is not punctuation, then I want T. So now all my punctuation should be gone, I hope. Yeah, there's no punctuation, right? I mean, this is a comma, but it's because it's a list. I'm printing a list out. There is a space. So space is not considered punctuation. So let me go back to, so let me add that. Let me fix that, right? Oops. Okay, so I say I want everything that's not punctuation, not space. Okay, right? So now this space should be going, after Balakrishnan, there should be no space, right? Do that. So Dr. Balakrishnan, where are you? Yeah, see? No space. So space is gone. So you see the idea lah. Okay. Now you can play around with these kind of conditions. It doesn't have to be exactly the way I did it. For example, some people may prefer to do if not punctuation and not space, and you prefer to do that, that's okay too. It's just the idea is you can filter out based on attributes. So that's the key takeaway, right? So we are doing a filter. We're using, when you clean something, you are just looking through. Imagine you are just looking through the whole list and you say punctuation gone, space gone, stop word gone, right? Okay. So I'll show you what the stop words are shortly, but get the idea here that we're just trying to clean by looking at every token. So this is where tokens are very powerful, because there's a lot of these little attributes. And we'll see what those are. There's a full list of them. Okay, but if you run this now, you should see that it's actually cleaned. Okay, I did not clean the case because you see there's still capital R, capital J, because spaCy knows how to handle it inside already automatically. I don't need to do it. Okay, it will be redundant work. Okay? So I cleaned the text. So before my text was a bit dirty, right? It's like has what? I cannot see. Okay, before my text had some commas, had some space. Now it's actually nice. Okay, so that's one stop. Now let's look at Chinese. How is it cleaned? Okay, same thing. I can use the same function. Just make sure you pass in the right model, right? So after you clean the text, you see that for those who can read Chinese, all the spaces are gone. The full stops are gone and all that. Okay, Chinese is not so. Chinese stop words are also gone. Okay, so this is a good segue for stop words before I pause. Okay, because I haven't really explained. I talked about stop words, but I haven't really shown you the concreteness of it. So here it is. Okay, so stop words are what? Okay, there is a list, hard-coded list internally in spaCy. Okay, so every language model. This is a language model, right? Has a list, a predefined list of stop words. Okay. Okay, what kind of words are these? well, if you see them, you sort of get an idea that these are very sort of like, words that you add so you make your sentence longer, right? It's like, afterwards, I will go have coffee. I mean, the meaning is I will have coffee, those kind of things, right? Or although this, although that, also is a very common one. So these are stop words. So these actually don't add too much to the meaning of the text. Okay. However, we also recognize that everybody's NLP tasks may be different, right? Maybe sometimes I'm looking at time or schedules, right? If I'm looking at schedules, then I want the word afterwards means a lot to me, after and before. So I may not agree with this list. I may say, I think I should include after and afterwards. So what to do? You can actually change stop words. So it's very easy. It's a Python set. That means it's something you can add and remove easily. Okay, so I just remove the word afterwards, then later it would not be considered as stop words. Okay, so the English stop words are sort of a suggestion. You can also choose not to use them. Okay, so so I think I will pause here for questions. Okay. They are stopping, so let me go up the list first. Okay, so okay. You run it directly from the link. You don't clone it in GitHub. Yeah, tokenizing, if you don't remove pronouns conjunctions. Those actually will, so we are doing three different things. Conjunctions, pronouns, and verbs are going to be in the exploration side. When we clean, we are just cleaning punctuation. We are cleaning spaces, and we may optionally want to clean stop words. Okay. When do we tokenize single words and sentence? We don't tokenize sentences that often. Most of the time, what we do is we tokenize by word. But when we want to process sentences, let's say recently I did a little project where I'm trying to tokenize some job postings, and the employees in LinkedIn would like to put the job postings in sentences, right? Like, responsibility is you have the bachelor's degree, that's one sentence. And the next one, you need to know C++. So I wanted to cluster the sentences rather than doing words. So that's when I use the sentence tokenization first, break into sentences, then I do my processing per sentence. Okay. So most of the time, at the end of the day, we would tokenize the word, but whether or not we treat the whole job posting or the whole news article as a giant article or sentences in articles. Okay. If our text has both Chinese and English word, we have to make a decision. So you can either say your text is mostly Chinese or your text is mostly English, or you can do both models. Basically, you can run the text through two models and just consolidate the results. Okay? That's if you have 50-50%. If it's like one or two words and then the rest is the English, then you can potentially just add rules. Okay, that's more advanced. You can just add rules. When I see this Chinese word, it always means this. Okay. The cleaning the text does break up the names. However, later on, I'll show you how Explorer, how spaCy looks at entities. Okay, so yes, the cleaning, the breaking up of the text into tokens is a very common step. It is not perfect, it's not foolproof, but it will at least give you a way to clean, particular tokens like punctuation. Then after that, you can combine the text back and do again. So just because I tokenize it doesn't mean that my original text is gone. It's still there. Okay, I can still combine the tokens. Okay? So last question is, what are stop words stopping? The term stop words is misleading. I don't know why they are called stop, but I think what they mean is they just don't add to the meaning of it. Okay, they don't add to the meaning of the text. So if I have a full Shakespeare play, the word thee and thou, okay, having the word thee and thou, it appears a lot, right? Because they are using Old English. So the most common word, it will be thee, and it's not really going to be helpful for me, right? I want the important words like, maybe Romeo, Juliet, love, those kind of things. Yes, you can, and you can add words. You can add and remove words from the sort list. It's a Python set. Okay, yeah. Same thing for NLTK. In general, stop words are meant to just be a suggestion based on the it's because these are built by NLP experts. So these are the words that they consider would be common stop words. However, you can always change them. Okay, I won't cover that here. It's really just a basic add and remove. Okay, you can look at this Stack Overflow link for the detail. Okay, so it's about 3:21. Let's actually have you, let's move on a bit and I'll have you try your own text. Okay, just press on for about 10 minutes. Then we can try your own text, because then you can play with this. This is even more interesting. Okay, because before that we're just, tokenizing. Okay, so exploring tokens. So what can we do with tokens? So internally, this NLP thing we saw earlier, right? We did NLP. So what did we do? Let me recap. Okay, the starting point of every spaCy program, okay, let me show up to where we really started. Okay. Okay, I'm just deleting these so it don't get in my way. Okay, so how did we start? How do we get here? Okay, we install, we reload, right? We started here, right? See, this part is very subtle, but really what this is we have spaCy and it's loading models. So NLP is a way spaCy calls language models. Okay, I know it stands for natural language processing, but they always, the custom is always to call it NLP. I have two of them. That's why I'm doing NLP and NLP ZH, right? So this is the language model. Okay, so I loaded this before any of this below has happened. This is just the model from, from the Python library. I haven't done any text. Then the very important step is this guy, right? This cell is particular line number 12. Okay, if you don't follow every single line of code, this is the one that I insist you have to at least remember. So you take the language model, you feed the text in, and you get a document out. Okay, let me repeat. So you have a language model, you feed a text in, and then you get a document out. Then from there, you can do all sorts of things with the document, right? Like get sentence, get stop words, remove stop words. So that's what happens in that pretty picture. So when we pass in a text into the language model, NLPEN and NLPZH, internally, it will tokenize, it will run all these tagging, parsing, NER, and then you'll spit out a doc. Okay, so that was the doc that we use for tokenization, right? We can get the tokens, we can get the sentence, and now we can get even more cool stuff. Okay, so we can get information about each token. Okay, so there's a lot of token attributes here. Okay, so the token attributes take a while to sort of read through. Some of them, I want to caution you, some of them may work, may not work. You have to try. Okay, so let me go to up to the page. Okay, this is the token API, very long page. Okay, token, individual token, like a word, punctuation, symbol, word, space. Okay, right. For example, right, NLP. You see this pattern? You remember this pattern, right? NLP text spit out doc. The first token is doc 0, right? We just happen to print all of them. So if I scroll down past all these are all the extensibility stuff. There's a similarity we'll look at later. Yeah, all these things is ancestor, conjuncts, children, left, right, up, down. I don't know, there's no up, down. Subtree, sentence start. Okay, so you can see whether it's the start of the sentence. I'm going very fast because I'm going down to the list, the table. Okay, so you can get all these attributes. You can get the text content. You can get the text with white space. Okay, you can even get the thing is pretty cool is you can get the base form of the token, lemma, okay, which is like the root word, kind of. Okay, then norm is to do with vectorization. You can get the lowercase form, so you don't even have to do your own lowercase. It already has it. Okay, right? You can get suffix, prefix. Well, so these are the things I used earlier, right? Some of these I used earlier to filter the Boolean things. So is punc is what I use. Is the token punctuation. If you don't if you want even more granularity, you can say, is this a left punctuation or the right punctuation? Because sometimes you want to see if some text is in between punctuations. Is space, is quote, is currency, okay? Is stop, whether it's part of a stop list. Okay, now we'll see this POS doesn't, it means part of speech, okay? Not usually means, not the usual meaning we say POS, part of speech, okay? And then we have the text, okay? So there's a lot of things to plow through, but I will just show you a few, okay? So you can print some token information like the text, part of speech, syntactic dependency, the ancestors, and all that, and the word vector. So if I do that for the very first, okay, now I've already gone through and cleaned the text because I wanted to see the words, the ones, I don't want to look at punctuation. Okay? So you see this text is jobs. Part of speech is a noun. 92 is just the ID that internally spaCy uses. Okay, okay, see. So you have the underscore, that means the actual string. It's a subject, okay, noun subject. And then actually, I'll show you later a cool way of looking this up because nobody remembers what this. There's a way to find out. Okay, you can ask spaCy. Then there's the ancestors are set and their children. And there's this very ugly looking thing called the word vector, which we'll look at in part B, but that is its vector. Okay, then you can go on. The second word is available, right? Right. And then you can also do for Chinese, right? The first word is August 8th. So no, not August 8th, August, right? It's a noun, it's a compound noun, ancestors, okay? So the part of speech text, okay, you can use them as filters, okay? So for example, I can say, so any tag here, right? I can use it as a filter as well. So if I want to just extract the nouns, for example, okay? So if I want to just extract the nouns of the document, okay. So again, I do this. This is the canonical spaCy use case, right? You take NL text, take the language model that's passed in, run in the text, and get the document. Now I add this filter, right? So I say I want all the nouns. If part of speech is equal to noun, then return. Okay. So now I get all the nouns. Okay. That's one thing you can do. Quite straightforward. You're just filtering, identifying the nouns. So if I say I want verb, for example, then you have all the action words, right? Facing, said, can, right? So you can do those, right? You can do adjectives. Okay. You can also do all the different part of speech in the document. This is a set notation. I think it's if you don't know Python, this is we can just skip over this. It's not that important. It's just to say, give me a set of all of the possible part of speech in this document. Okay, and do for Chinese. Okay, right, and you can actually trick it. So here's the cool part that I wanted to get to. We want to trick this part of speech tagging. Okay, so look at this sentence. Okay, she thinks fast when she had a fast. The correct beat must be beat. Okay, so if you recall, fast is a what? It's not a noun here, right? This is a noun. Fast can be a noun or a adverb, right? Or adjective. Same thing. Beat can be a verb or a noun, right? This is a noun, this is a verb. So I was just testing it. So I just returned the part of speech and the text for every document just to see whether it's able to be tricked. Okay. So, and you can see that, oh, okay. The first thing is a space because I had this extra space here. I can delete that space. Okay. And see that actually spaCy is not just doing a static mapping. Okay. He's not always saying that, every time I see the word fast, it will mean this part of speech. Actually, it depends on context, right? So fast is a noun here. It's an adverb here, right? And beat is a noun here, but it's a verb here. Okay. So those things are sort of important. For a good language model, it needs to know the rules, right? So there's extra things here, there's extra space. That's because, you see, I didn't clean this text. I just used it as is, right? I could clean these things. Okay? either by changing the text or by using filters. Okay? And the last part, okay, this is the coolest part, which is the spaCy. Okay, so spaCy has this thing called visualizer called spaCy. Then I will take a break because it's at 3:30. Just nice. So it's nice that I can just dump all these and write code, but if I'm not a coder and I just want to see what is spaCy found for any text, I want to just kind of visualize it, I can simply just use this spaCy to do it. Okay, so what I did was I took the whole document, okay, the whole jobs are available thing, and I say I want to show the entity, which is, and I want to recognize entities like person and date. And I say, please render in Jupyter. Otherwise, this is going to render in a web server. So this says, please render inline. And this is what I get, okay? So later on, when you try your text during the break, you can actually explore to see whether you got everything right? So jobs are available for Singaporeans, which is a entity. Next 3 years is a date, it's a type of entity, right? Cool, right? It's not just 3 years, it's the next 3 years. Vivian Balakrishnan is a person. So earlier on, there was a question. We split every token. Now it's just Vivian and Balakrishnan. One is a woman's name and one is a, surname, right? Or, so now actually it's not lost. You can actually still get the entity because it's part of the document, okay? So all that, okay? So I'm going to pause here. You can look at the entities, but you can also ask spaCy to explain. Because I'm too lazy to look it up, right? I just use spaCy.explain. spaCy.explain, I say, what is NORP? I don't remember. Or like here, what is GPE? I don't remember. Okay, memory not very good. Okay, so I can ask it to explain what it is. Okay, it's like, oh, it's country, cities, or states, right? And part of speech text, you can also ask it to explain what a PROPN is, proper noun, or just now I was like struggling with this, right? I forgot. It's an adjective, adverb, blah, blah, blah. It's an adverb. Okay, so we'll at least map these texts and you can try Chinese. Okay, so let's take a short break. I have you try your own text. We'll break for 15 minutes. Okay, and then after that, when we come back, I'll address questions because I think you may have more questions after you try it out. So if you are not in the mood to try, that's okay. But for those who want to try, we shall pause. So let me set a timer. Okay. Let me set a 15-minute timer. So I'll give you some time to play with it, okay? Okay. And I'll show the timer as well. Okay. So we have up to we can start at around 3:45, 3:46. Okay. So we share screen. Second. I just share all my whole screen so you can see both the timer and the thing. Okay. Share my entire screen. So I have about 15 minutes. How do you do this? Basically, if you have been following me in opening this in Colab, okay, this notebook, opening it Colab, right? So if you do bit.ly and then ISS text 101, right? I went through this process of loading it Colab and all that. If you follow it along, you can actually replace your own text up here. Okay, so where you see where I added all the way to the beginning, where you click, let's see, tokenize some text. Okay, so this is the magic place to start because before that, assuming you have loaded the runtime and got bypassed the error, right? So you need to run all these here. Okay, and then here's where you can try your own text because earlier on I did show like if I don't want this text, like if I go, let's say if I go to, let's say I want to just tokenize spaCy's own documentation. Let's do this, okay? So I take this text, copy it, Okay, right? Copy whether English multitask, blah, 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 and then just like put it here, right? Okay, paste it and then run. Okay, then I'll just continue on, and you see that now my words are different, right? So you can just keep going all the way until the intermission, and you should see your own text here. Okay. Yeah, so that's sort of straightforward. So I'll show the timer. So we're about 13 minutes, and I'll be back. So the next part, we're going to switch back to the slides briefly, and then I'll just cover word meaning. This is where it may be a little bit more advanced. So don't worry too much if you're not able to get word vectors. It sort of helps to paint a picture of how these words are being represented internally. And reason why I like to introduce word vectors at this point is because spaCy gives you them. You can get them from spaCy and you can do some interesting things with them already. Okay, so and they got to do with word meaning, right? So what is so where we have gone through basically processing text, this part. Now we're going to go to the next part. Okay, finding meaning and comparing meanings. Okay, and we're still using the language model at this point. So what is meaning? Well, it's a loaded question. Basically meaning is what the word, I guess the definition of the word, what is intended to be. And in general, humans, we learn them, by experience. We learn them by talking to other people. We learn them at school. And we also learn them by reading and writing a lot of text. And, so this is a meaning from dictionary.com. In order for you to represent this for a machine, you cannot just give this a bunch of text. You can't just pass this to the machine and say, okay, the meaning of this word is, blah, blah, blah. This when it's a noun is this, and when it's, I mean, the machine is going to just, spew an error or just give it back to you. So you have to find a way to represent meaning, okay? And one of the most common ways to represent meaning is to use numbers, because machines deal with numbers, right? So what do? We take this meaning, right? Somehow find a representation of it in numbers. And as you may have realized, we use a lot of text to train NLP, right? So how does the model know what is an entity, what is a token? It's learned through text. So you can also likewise learn meaning through text, and in particular through context. Okay, so basically relationship of the word with other words, and other subjects. So it's a bunch of numbers derived from learning. And this learning, I'm using the broadest possible definition. So it could be machine learning. It could also be by rules. Okay, it could be by statistical models or probabilistic models. So it's not only ML specific. Okay, but the key is it's still on large volumes of text data, because the numbers are not going to be, they're going to be random. If you are just using one or two text, they're only going to be able to represent the meaning from that one or two text files. So you need to give it as much generalization as possible. And numbers are good because they are useful for machine. They can be, you can do arithmetic on them. You can find out direction and magnitude. You can compare them. Okay, most likely you can rank them. So you can rank words based on meaning and similarity. So the word vector for the word meaning is from spaCy is actually 300 entries long. I've only given about the first maybe 30 entries. Okay, so it looks like a bunch of gibberish to a human. Like, this is 0.3, 0.03. This is 0.1, right, to the power. So, I mean, even I cannot read this. So one way to visualize it is to sort of paint pretty pictures like this. Okay, so we have this is a word vector, the same vector earlier. Okay, I just color coded it based on the value. So negative numbers are dark, positive numbers are light, right? So you see the word meaning is actually just a bunch of numbers. And then the values are all over the place. Like the dark negative values are like sort of in bands. Okay, so it doesn't alone, if you don't look at the two below, you just look at this, I cannot make head or tail of it. Like even if I give this to a machine, right, he's just saying this is just an array, it's a number. But what I can do is I can compare. So it becomes significant when I can compare with somebody else. Just like numbers are relative, right? Numbers are significant when you can compare them or sort them, multiply them. So when I compare with a synonym that I know gives the same thing, same definition or same meaning, then I can just see, oh, it looks quite similar. How come? Like the bands that are like sort of similar, it's not exactly the same. Okay, it's not exactly the same because this word is probably used in different contexts from this. This is maybe a simpler word, more often used in conversation. This is maybe more formal, right? Used in speeches, in, I don't know, more scientific or like literature texts, right? And then if you compare to something else, banana is like a favorite example in spaCy. If you go to look at spaCy examples, you see banana everywhere. Okay, so you see banana is very different, right? But you can tell that these two are just by the color, like not even caring about the magnitude, the number 0 to 294, or the 0, -1 to 2. You just look at the colors, you see that banana is a completely different thing, right? Completely different meaning. So this captures the meaning of banana. This captures the meaning of meaning and definition. So it's an encoding, it's a semantic encoding. The numbers are come up through basically looking through a bunch of texts, looking at words before, after, looking at words that can be good with surrounding words, right? So these factors encode semantic meaning, okay? So how are they generated? I kind of got into that a little bit earlier. Two ways. One is probabilistic and one is deep learning. This is just a bunch of words, but what I'm saying is basically you can estimate probabilities, how often words appear together, okay? Right, you can try to maximize that probability and get the word vectors, which are parameters. It's just, think of it as an equation that you use a method called maximum likelihood estimation to estimate the best parameter that will maximize probability. So this is a maximization problem. The second one is a deep learning problem where you do a related task where you try to predict a word from nearby words, either missing word in between or words surrounding it, neighboring. Then you just extract some representation which will be generated as a byproduct of this task. As a byproduct of this task, right, when you try to predict a word, you kind of have to learn, the machine has to learn the meaning or the context, especially from nearby words. So it just takes this part becomes a word vector. This one is not the word vector. This one is just how the probabilities are sort of set up by GloVe. Okay, they are just trying to compute all these probabilities and maximize them, and then the result is word vectors. Okay, so it's just a bunch of processes going through to try to figure out how do words appear together, right? Because words that are nearer have similar context, have similar meaning. Words that are far away generally don't have similar meaning. Of course, there are exceptions, that they're long sentences, but we are trying to predict the 80% case here. Okay, so we're going to see how word vectors are used, and then we'll go into a demo. Okay, so we compare how word vectors are used. They're used for comparing with other texts. So we recall earlier we had the 2 word vectors and then banana. So we compare, right? Banana is going to be very different. So you can compare just by looking at the distance between the 2 vectors. Okay, how near are they? You can also pass it into neural networks to perform classification or regression tasks. So for those who are familiar with machine learning, who understand what this means, basically the word vectors are just numbers you can pass into more algorithms. Okay, more algorithms, like you can do the Twitter sentiment, right, for US airline. You can classify documents because the meanings are captured, right? You can also do clustering, which is grouping similar documents to find patterns. So the word vectors, the numbers will be quite near, right? Here the numbers are quite near. Here the numbers also quite near or far. This one is the numbers represent meaning. Okay, so those are very, very common ways to use word vectors because they are just machine consumable. Okay, so let's just quickly look at how do you compare meanings. So for humans, we go based on our human knowledge. We go and ask our parents, ask our teacher. We also may go to look at a dictionary. Dictionary has synonyms for common words. So we have a preset list. Okay. Machine doesn't have this. Okay. Machine only has this, right? Or more, actually more like they have this. Okay. They have this bunch of numbers. So how? Well, this is where it gets a bit more messy. It goes into vector, basically vector operations. Okay. So you treat it as a vector. Okay. So let's say this is my word for, I think I have an example next. Okay. So just say this is two vectors. I need to compare how far away, right? So I can either measure like the tip. This is a vector is usually a set of coordinates here, right? And then the tip is here. Okay. So this is, let's say this is the word banana and this is the word meaning. Then I just measure how far away is the two tips. Okay. I can also measure the angle. So if something is very different, the angle is going to be bigger. If something is going to be different, this D is going to be bigger. Okay. So this is a lot of words. Let me just demonstrate here. Okay. So earlier on, you saw my three bands, right? My three bands. Let me just go back. So you see these two. These two look very similar, but human eye, right? This one very different, right? So how do we capture this in terms of an operation? Okay. We actually treat them like vectors. So the vector for meaning, let's say is this vector, which is basically, this is the origin, 0, 0, right? And this is just the 300 word point. Okay, so imagine this point is 300, has 300 numbers, is a 300 dimension thing. Okay, okay. So it's the two vectors are going to be very near. They're going to look very similar when the distance is small. Okay, because this one is just only going to point just maybe a little bit away. Okay, so think about it this way. So you see, right, if I want to change from this number 1 to number 2, what do I need to do? I may just need to add a bit of color, minus this color here, right? Then I need to maybe add a bit more color here, dark color, add a bit, like I just need to change very little. So the distance, the edit distance, which is a term we use a lot, also in comparing text, editing distance. So how much you have to change from one to another is very small, right? So that is what is captured here. To change from this to this, I just need to make this change and it will move, conceptually will move the vector here. So they are very close, right? The other one is very far. So meaning is here, same purple, and banana is very far. So this distance to change this guy to this, right, is a lot. There's a lot of changes, right? You see, from if I want to change this one to this one, I need to like maybe, you know, make the color more wash, so like more orangey. So that means I need to add more high numbers. So every single entry, so this is an entry from 0 to 300. Okay, every single one I need to change, right? So every single one, this guy, right? The first one is 0.03, right? I may need to change it to, you know, 0.5. That's why I may need to change to 1 point something, 2 point something. You know, I need to change every single number. Okay, so I need to change every single number. So the distance is very far. Okay, so we do a very simple calculation called Euclidean distance. Okay, so Euclidean distance is like your Pythagoras theorem, where you just compute x squared plus y squared and then you square root. It works in high dimensions. It works in 300 dimensions. Okay, I should also say that distance is relative to a reference word. Okay, so in NLP, we compute similarity. We don't just compute meaning standalone. It has to be a reference word. Okay, so keep that in mind. Okay, so how do we, any uses of it? We extract meaning, we do word suggestion, we do compare. Let me come back to this later after we do the hands-on. Okay, so we're going to look at the comparing the word vector and getting the word vector. You don't have to do anything here because it's really sort of technical, but you can just see what I'm trying to do. Okay, so second part, okay, we are going to get the word vector. So I just did a demo of meaning. Okay, so I just passing in the text meaning, right? So that's how you, this is the pattern, right? You can pass in any text. Don't have to be the original text. Just any text pass into the language model, you get a document for it. So this is the meaning, document for meaning. And the vector is this thing that I had in my slides, right? 0.03 and all the way. So that is the vector. Okay, so this is how the machine has defined meaning. Okay, So if I plot it, so in this fancy, not so fancy, I just use a heat map to plot it. I plot the vector here. Okay, I plot the vector. Okay, and I get this. Okay, so it's just a heat map. So every value will have a color based on the value. So the very first value here, right, is 0.03. Then the next one is something else, right? So every value here has an entry here, right? Starting from the very first value all the way to the end. Okay, so this is how the slides look like, right? So I can repeat the same for definition, and I can notice that they're all similar looking. So to change from this vector to this vector, I just need to change maybe a few entries here. This one can largely stay very similar. I'll get close enough. Okay, I won't get exactly, I'll get close enough. But if I try banana, so I plot the work vector for banana, and it's like, wow, it's completely different. There's like this very high, significantly negative value at 140. Then there's all these are like around in the between 0 to 1 or higher than 0.1. Everything is higher than 0.1. So if I want to look at it in more detail, you can actually see. So if I just go back up there and see the word vector, so let me just get this code and I'll paste it down here. Okay. I will be wrapping up in about maybe 5 minutes. Okay. For those who have to leave early, go ahead, it's okay. Okay. So I will try to wrap up in about 5 minutes. So I'll show you just how to get the vector for banana. Okay. So, and you can see that the values are very different. See, this is higher than the first value. Is in the 0.2 range, right? Compared to the other one is 0.03. That's why the color is orange, right? So this is a different definition. Okay. So again, repeat for strawberry. So that's the word vector. Let's say display. It's only for displaying. It's only for fun. But what we really want to do is compare. And here is slightly technical, but you can use Euclidean distance, or you can use similarity. Okay, distance higher means further, right? Remember the slide earlier. Okay, distance higher means further. Okay, or similarity means more similar means smaller distance. This is just two ways of measuring it. Okay, spaCy uses similarity, but I think Euclidean distance is a little bit more like more layman. So I'll just use that just a show. Okay. So ignore the huge chunk of code, but just see, I'm just computing distances of two words, meaning and definition. First one is the Euclidean distance. Second one is the cosine similarity. Okay. You see that, okay, not much meaning not much I can see from this number is like 4 and 0.6, right? But if I compare with another word like banana, you see that the distance is further, right? See that? You see the distance? So banana is 7 units, right? The units are in the vector values, okay, away, whereas meaning is 4. So this is quite a distance further, okay? And it's less similar. So lower number means less similar. Strawberry and banana is closer, right? Because they are fruits, right? Probably used at the same text. See how strawberry and banana, the numbers is sort of like almost similar to the meaning and definition. So these two are synonyms. This one is not synonym, but same category, quite near. Okay. And then for those who know Chinese, you can do the same. Chinese, teacher and student. Okay, stand alone, don't really know, but if you compare with teacher and president, okay, teacher is very far from president, less similar. President and election, because it's, election season, quite near, right? So those are the things you can do, okay? So let me check questions. Okay, so let's see. Okay, can we compare meanings with two different language models? Not so easy, yeah, because the language models are trained separately. So you will just be comparing apples to oranges. Sorry, that's a bad example. We just talked about strawberry, banana. You can treat them like two completely different language models. It's not comparable. See, because you see, it's shown here, the Chinese one, right? See the distances of the word vectors. are in the 40s and 60s, whereas here the distances are here, right? You can probably use the similarity, but I sort of question it. It's don't put too much stock in it. You can use it as a rough gauge, but if you get down to the decimal point, like all the way here, and you say, oh, it's 0.003 difference is a big deal, then it will be a little bit reading too much. Okay, so cosine similarity is basically measuring, so similarity, I should clarify, right? The higher, the better. More similar, right? Higher is a more similar. So you want a number. 1 means perfect similarity, right? 0 means no, different, right? So, so for distances, it's an opposite way of reading it, right? Higher is further, right? So less similar. So it's opposite. Okay? These are very common terms. Okay. Okay. So let's go. Keep going. Conditional probabilities are used as a basis. Yeah. They compute conditional probabilities because it's given a word banana, what is the probability that strawberry is going to be there? It's going to be the next word, right? Or given the word president, what is the probability that election is going to be the next word? Yeah. Okay. So I think I will wrap up here. The rest of it is just demos of how to do similarity. But I think what will be useful is maybe wrapping up in terms of what you can do next. Okay. So we've done getting and comparing. Okay. So we've taken really baby steps, and 1 hour, 1 hour and a half hours is not even enough. Okay. We didn't even get to let you do the hands-on because I wanted to spend more time in the basics, because without that, this is moot. But hopefully this will get you started. I'll just give you some resources. Okay. Now, spaCy is wonderful because they have a whole universe of projects and libraries you can use. So once you sort of start to understand spaCy, you can go to the spaCy universe. Okay, let me just send the link because this is quite exciting. Okay, I don't work for spaCy, by the way. It's just that they've been doing a lot of good work. Okay, and they're sort of the most accessible for entry level kind of thing. Okay, so it's okay. So this will show some even some companies who have built applications, like Ellen NLP has built on spaCy. So spaCy is definitely used in an industry. There's a lot of things you can do. We just tried spaCy just now, right? So there's so many different libraries you can try. So it's just a starting point. There's a very exciting space. So you don't have to build everything from scratch. You can actually try things. Okay. Another thing I want to point out is education. So there's a free spaCy course. Okay. This one is very useful, especially for those who have questions about how do you extend the NER, name entity recognition, to add new entities. How do you extend phrase? The matcher. So check out the basically I think the advanced, this one. There is a little bit of adding matching rules, adding rules here, chapter 2 and chapter 3, like simple rules. You don't have to go through to chapter 4. Chapter 4 is a bit daunting, but if you know how to add simple rules using matcher, you can already handle a lot of things. Okay, you don't have to be a neural network expert. In fact, I think there's probably a time sink at this point, unless you really want to try. Okay, so that's one thing. So again, I already mentioned the online course. NLTK people, if you're interested in NLTK, there's a free book. You probably already know about this. But even better is there is a graduate certificate by NUS ISS by our data science team. Okay, it covers 27 days. Each one is a separate course. So you can take this course, then later on take this course separately. So it covers a lot of the things. We started touching just the basic of the text processing here only. But you can take a course for it, a full course, 4 days. Then you can go into text sentiment mining. So it's a highly recommended course. It also counts towards an MTech. So if you take the course and you later on want to do an MTech and deepen your qualifications, you can get that too. But if you finish the 4 course, you get the grad cert. Okay, they do not. This team didn't ask me to promote. I'm just promoting because it really is relevant to you if you are here. Okay, and then upcoming courses at StackUp, we have a starting 4th July next Saturday. We have a 4-course series for part-time. The details you can go to this link, or you can just later you scan the QR. I'll just send this link. It's just a short link for StackUp. Okay, because our courses can be so hard to find sometimes. So let me just do that, and I'll close. Okay, so I call it ISS StackUp. It better work. Okay, so if you click on the link, it'll take you to this page because it's a very long URL, right? But it shows you the different courses, AI and cloud and all that, and the courses for that. Okay, the grad cert you have to Google. It's quite easy. You just Google grad cert in practical language processing. I think I'll send the link also. Okay. ISS, yeah, this guy. So there's more details in this one. Let me send this on the chat. I do not have a short link for this, but I think this will suffice. So give me one sec. Okay. So those are the things you can look at. Again, they didn't ask me to promote, so it's not specifically for this, but it's quite useful. So that's all I have today.